So, so we talked about orders the last time. I'll just define it once. We won't go over the the properties we discussed last time, but if needed, we'll just use them. I mean, I'll just mention them while we're solving a problem. So we said that if A and P are co-prime, okay, let's not use P. Say A and N are co-prime, then and let's just say N is at least 2, A is not 0, then we say that we see that the order of A modulo N is the smallest natural h such that A to the h is congruent to 1 mod n. I'm just defining it. I'm not going through the properties. So here's a question. Okay, and here's one property that we didn't prove, but we'll use that. Okay, and then okay, so that we just also put these definitions at least. We define what the primitive root is, right? We say, okay, so we have A and so this condition will hold true in general. So I'll not write that again and again. So we also said that A is a primitive root mod n, also called a generator. Mod n. Uh, if the order of A is phi of n. Uh, I use the other phi. I keep using this. Okay. So we have these two definitions. And one theorem that we did not prove, but I just mentioned it, is this that so okay, so we did see that not all natural numbers have a primitive root, but all we need is that n, okay, n at least 2 has a primitive root if n is one of the following: 2 or n equal to 4 if one of the following is true. Um, holds n is 2, n is 4, n is p to the k for some odd prime p, and some natural number k. By naturals, I mean greater than or equal to 1 and integer. So we won't count 0 as a natural. Or it's twice a power of a prime. Yeah, and we won't prove this. Yeah, so note that in particular, this includes all primes, which means all primes have a generator. Okay, great. So let's start off with a very basic problem. So how do we show this? Okay, we want to show that. Uh, okay, we want to show that. Um, okay, suppose p is an odd prime. Show that there exists a natural n such that p divides n squared plus 1 if and only if p is congruent to 1 mod 4. How do we show this? I want to use the idea of generators, by the way. Is the question clear? I've just written sort of shorthand. So by this I mean there exists a natural number n such that p is a factor of n squared plus 1. This is true if and only if p is 1 mod 4. I just want to get started with this first. Any ideas?
Let there be a generator G, then
Okay, so we have a generator G. Okay, so G is a generator modulo P.
we'd need G to the k is equal to n, then G to the 2k is congruent to negative 1.
Yes. So we take a generator G and we know that okay, so if such an n exists, it definitely must be coprime to P. So we consider any n mod P. That's the same as considering G to the K for some K, because the point is that a generator generates, so this thing generates all numbers modulo primes. Well, okay, here it's just P minus 2. This set and this set is the same mod 2, mod P. Okay, so n is G to the K. And then, so what do we want? So what does this translate to? This translates to saying there exists a k, integer or natural, doesn't matter, such that p divides g to the 2k plus 1. And now what?
We have G to the 2k congruent to negative 1.
Yes. So this is the same as saying, okay, so let's just simplify this part, right? So what does this say? It says g to the 2k is minus 1 mod p. So what next?
So G to the 4k is 1.
Okay, great. And then
So then we have that p minus 1 divides 4k but doesn't divide 2k. And then we're done.
y?
Because G is a generator.
Yes. Good. Yeah. Yes. Yeah, that's it. So, okay. So note that we get g to the 4k is 1 mod p. But remember that g is the generator. So the order of g mod p is p minus 1, right? And what is the most sort of crucial property of orders? The point is that the order will divide this, because for any number a, and so for any coprime a and n, if it is the case that a to the k is 1 mod n, then the order divides this k. This is true. And so the set of exponents k such that a to the k is 1 mod n is the same as the set of multiples of the order. And so note that g to the 4k is 1 mod p automatically implies that the order is a factor of 4k. But from here, we also know that the order is not a factor of 2k. And so, what can we say from these two? So, there's a number which is divisible by another by 2k, and but not divisible by 4. Sorry, divisible. Okay, it's a factor of 4k, but it's not a factor of 2k. So, what can we say about p?
P minus 1 is a multiple of 4.
Yes, exactly. So, note that from these two statements, we can actually say that p minus 1 is a multiple of 4. Does everyone see why? So let me know if you don't see this. And it makes sense, right? So, for example, if 4 was not a factor of p minus 1, then there's nothing about 4k that makes it a multiple of p minus 1 that 2k did not have, because 2k has all other prime factors the same as that of 4k. It's only the power of 2 that is different. And so if 2k is a multiple of, not a multiple of p minus 1, but 4k is, then that must happen because of the factor of 2. So the power of 2 in 2k not being enough to be a multiple of p minus 1, but the power of 2 in 4k being enough to be a multiple of p minus 1. And so the power, in fact, the power of 2 in 4k and the power of 2 in p minus 1 should match. And that actually means that 4 is is a factor of p minus 1. And so this implies p is 1 mod 4. What about the converse? So we've shown one direction. We've shown this. We've shown the harder direction. What about the other side? So now I want to show that if p is 1 mod 4, so this was this side. Now I want to show this side.
Can you
This
tell the part why you assumed when B equal to G to the K?
this
Oh, yes, yes.
Yes. Uh, so the point is that any natural number coprime to p can be written as g to the k mod p. So this is actually g to the k mod p.
Oh, actually, I read it as equal. Sorry.
Yeah. So for some integer k. Yeah. So but it doesn't really matter. Yeah. As long as it's congruent to the congruent mod p, it should doesn't matter. Yeah. Okay. So what about p being 1 mod 4? How do we show that there is an n for which n square is minus 1 mod p? In fact, if you have a generator G, you can explicitly find such an n.
I cannot tell.
Yeah, sure.
So we get it is mostly the reverse. We get that P minus 1 is a multiple of 4. So implies like if G is the generator, then the final number of the generator, uh, like the order divides the final power of generator.
Uh,
Like G to the 4K will be 4K will, we can take any 4K such that uh, P minus 1 divides that 4K. Yes, yes. And then we can have that it is equal to 1 mod 4.
uh, yeah, but where is the n whose square is minus 1 mod p? I'm still like, where do you get the n from? I mean, I want to show this, right?
We can put for K for some any even. Uh, even in natural numbers, then we can factorize e to the 4k as some n squared.
Mm, not sure what you mean. Okay, so we have g to the 4k minus 1 is 0 mod p. So you're saying that we can factorize this, which is true. We can factorize it as follows. But now what do we do? Like either of these two quantities could be a multiple of p, right? So why is this not 0 mod p? So if this is 0 mod p, do you see why we are done? Because we can just
Can
treat
I
n.
tell why this is not mod 0 mod p?
Yeah, sure.
But then g to the 2k will be also congruent to 1 mod p, implies
Okay.
that p minus 1 is also dividing 2k.
Yeah, which is a
But it is
contradiction.
not possible. Yes, yes.
Yes. So note that g to the 2k minus 1 cannot be a multiple of p because 4k is the smallest number. 4k is the order, right? So the order of g is 4k, p minus 1, which is 4k. So it's not possible for g to the 2k to be 1 mod p because order by definition is the smallest natural number. So this cannot be 0 mod p. And so this has to be 0 mod p. And so n equal to g to the k works, right? Because g to the k squared plus 1 is g to the 2k plus 1, which is 0 mod p. So this works. So the key idea was to notice that n squared plus 1 is a factor of n to the 4 minus 1, right? I mean, that's the key idea in both things, right? Just to convert it to something raised to something is 1 mod p, and then noticing that the power is a multiple of the order of the base. Okay, so I mean, this is like a property which is quite famous. So you might have seen this before, but it's good to know anyway. Okay, so let's move on to another problem. Okay, uh, find all naturals n such that n divides 2 to the n minus 1.
Can attempt.
Let's wait for more people.
Okay.
So just think in terms of primes. So uh, think of primes. Ideas? So okay, so we have a prime factor of n. What can we say about n? Like what can we say from this relation?
Uh, can I, either that prime is of the form 2 to the n minus 1 or 2 to the n plus 2 to the k minus 1 or 2 to the k plus 1. So,
Why?
because if we see remainder modular, there has to be either at least one prime of each type, of the type 2 to the k minus 1. Like of being 2 to the k plus 1 is not necessary.
Sorry, I don't understand. So we have P divides N. What is the next step? Okay, so we get 2 to the N congruent to 1 mod P.
We have that order of two with respect to p divides n,
Order of 2 with respect to P divides N. Okay.
and it holds for all p that divides n.
Yes. Yes, that's true. But what do we do with this now?
But it will be p minus 1 itself, so p minus 1.
Why is this P minus 1?
Like order of any number with respect to p, which is co-prime to, no, not up to.
Yeah, that's not true. Order of 2 with respect to 7 is 3, right?
Yes, that is not true.
Yeah. But do we have an upper bound on this?
Yes,
What is it?
it is p minus 1.
Right. So we have an upper bound of P minus 1 on this, right? So what this means is that if a prime P divides N, this implies that, okay, also the order of, first of all, note that N must be odd, right? If N is at least, if N is, so N equal to 1 obviously works. And otherwise, if N is at least 2, then N better be odd, because otherwise 2 to the n minus 1 is odd. That it's true because 2 to the n minus 1 is odd, so n must be odd as well. And so this prime P is odd, and so the order of 2 with respect to P must be at least 2, because it can't be too small. It can't be 1, because 2 to the 1 cannot be congruent to 1 mod P. This is absurd, because that means P is a factor of 1. So I mean this is true. Yeah. And so this order is at least 2. So what this means is, if I have a prime factor of n, then I have another factor of n which is between 2 and p minus 1. And this
We can
means,
take the smallest prime that divides n.
yes. So, but just by going by this itself, what this means is, so if I take a prime factor of d, pick a prime factor q of d. So what this implies is that I have another prime q between 2 and p minus 1 that divides n, right? More importantly, it's strictly less than p. So we started with the prime dividing n,
But it
and
cycles goes on.
yes, exactly. So we get to another prime. Actually, let me call it p prime here, where p prime is a prime less than p, and then we can go one more step and get another smaller prime, and then another smaller prime, etc. But we cannot go on forever, right? I mean, if we start with P, this should terminate after P steps at most. But it seems that we're going on forever, but that's not possible, right?
So it
So we have
implies
a
n
contradiction.
is some t itself.
I'm sorry.
So it implies n is some prime.
It implies that there is no such n, right, which is at least three, because every number other more than one has a prime factor.
But if the prime factor itself, then it doesn't make sense, I guess.
No, but the logic didn't use the fact that n is composite, right? I mean, I never assume that. So, I mean, we do have a contradiction, therefore, right? I mean, it makes sense, right? So, if n is the prime itself, then here itself, I'm saying that the order of two with respect to p is a factor of p,
Yes, that makes sense.
which, yeah, we'll get a contradiction in the first step itself. Yeah. Okay. So we have a contradiction, and so the only solution is one. Therefore, n equal to one is the only solution. And so we have this idea that comes up a lot. So note that we could also have just taken p to be the smallest prime dividing n, and the same idea works. Like we just stop here itself, because if we take p to be the smallest prime dividing n, then here itself we can conclude that there's another divisor of n which is at least one and less than p. But that cannot be, because the smallest prime number dividing n is actually the second smallest factor of n, right? Because the smallest factor is one, and the second smallest is the smallest prime dividing it. But this gives us a factor between the smallest and the second smallest uh, divisor of n, which is a contradiction. So this sort of combined extremal ideas with plus whatever order residue theory we know. Okay, let's try another problem. Uh, let's try something harder than this. Uh, okay, yeah, we could try this. So we have, okay, so find, actually, let m n be natural numbers. Prove that there exists an integer c such that c times m and c times n have the same non-zero decimal digits.
So we need to prove that there exists some c such that if we multiply some m and n to it, they become congruent to modulo 10 any power of 10. Which is,
Uh, no, that's not what we want to show. I mean, uh, um, I mean, sorry, what do you mean? Could you say that once more?
like if they have all the same decimal digits, then it implies they're congruent modulo and any power of 10.
Uh,
What does this say, what does it mean when they say the same non-zero decimal digits?
It's just that the set of decimal digits. I mean, it's just saying that the set of digits that are non-zero is exactly the same.
Oh,
Yeah, I think that's what it means. Let me think about it.
Do you mean it like some for some first digit it is equal to the second first digit of the other number, or they
I
use the
think that's
same set
allowed.
of
I think
numbers?
I think this question just says set of digits should be the same. It's
Can you show some examples so it becomes
like
clear?
like for example, like 203103 and 33120 have the same non-zero decimal digits. Yeah, I think so. I don't think they need. I don't think I need the order to be the same. But let me actually think about it. I mean, that would be a stronger theorem. If this turns out to be trivial, then maybe we can try that. Yeah, but it's just saying that they both have equal number of ones, equal number of twos, up to equal number of nines. But the number of zeros can be unequal. Yeah, so let me just write down what I mean by this. That that is for each digit in 1 to up to 9, Cm and Cn have equal numbers of digits equal to.
If we prove it for M and N are co-prime, then it will be proven for any M and N.
True. Yes.
Can you give some hint related to how to use generators here?
Uh, uh, I mean, it's for okay. So I I guess I guess you should try to prove that you can. There is a C such that I mean, not just permutations, but you can have like long blocks of like same digits. Maybe lots of zeros here, lots of zeros, lots of zeros, and then a block of numbers.
But that's what the question asks.
Well, not really. I mean, I'm saying that the number of blocks can be very few, like 3 or 4 blocks would work, where these blocks are all permutations, like sort of like this. Maybe these two are the same or something of that sort. So, so think of, so don't think of like generally too many permutations. Maybe just try to think of big blocks that you can make. Like, maybe you can write this as 10 power something times this plus 10 power something times this block plus this block. So x y z, and then maybe you can write this as 10 power a prime times x plus 10 power b times z, right, and plus y, something of this sort. Like, don't think of too many blocks. Like this would do, where a prime b prime are large enough so that these x y z don't interfere with each other. Maybe just try for certain numbers, right? So can you, yeah, just pick some m and n, and maybe we can try those first. like think, okay, so like you can think of things even simpler than this. Like can you think of finding a C such that Cm is just taking Cn and then like moving this digit, the last digit to the front? Is something like this possible? Like think of very simple, like instead of general permutations of the non-zero digits, can you just move around one digit? Like maybe we can try this. If this works out, then it's great. So I have no idea if this works out or not. So yeah, we could think of this. So okay, suppose I wanted to show that this is possible, then how will I formulate this mathematically? I want to show that there is a C such that Cm is obtained by just moving the last digit of Cn to the front.
So we get that Cm is concurrent to 10 to the k minus 1, that last digit into that last digit modulus
Okay,
C.
okay. So uh, okay, yeah, let's try. Sorry, could you say that once more? So
Like let the number of digits of Cn be some k. So
okay,
we
so
get
suppose.
that Cm is equal to, yes,
Mhm.
yes.
Yeah,
We get that Cm is equal to Cn
yeah.
minus that last digit d
Mm-hmm.
plus 10 to the k into d.
You're
10 to
missing
the
one
k
thing.
10 to the k minus 1.
You're missing one more thing.
What?
You'll have to divide this by 10. Right? Does this make sense?
Yes.
Yeah. So we subtract d, divide by 10, and then put a d in the front. Right. So that's what we're doing here. So so all we want is to, so we're just asking, does there exist C such that this is true? And we'll allow like something like leading zeros. It's fine. It doesn't matter. In fact, if we don't allow leading zeros and we take m to be more than n, then this Cm can be at most 10 times Cn, right? Because the number of digits in Cm and Cn will be equal. So if we better allow leading zeros to not fall into that case. But okay, I mean this is fine. And now what do we do now? How do we deal with this? Because this k is tied to Cn, right? It's not like k is independent, or is it? So to know that since we
Can't
allowed
be dependent. It is dependent on C.
what?
Like the k is dependent on C. Dependent.
Yes. The point is that I allow leading zeros. So I can take k to be any number which is larger than number of digits in Cn, and that would work. For example, if my Cn is equal to, I don't know, something like 423, it's not a problem if I make Cm to be something like this. Of course, this may not work, but it's fine to take leading zeros here. That's what I'm trying to say. So we could take leading zeros and then transfer the C here. And so our K is not just 3, right? I can, here my K is 8 actually. So it's, so yeah, we could always do that. Yeah. So K is at least greater than the number of digits in Cn. So we can sort of treat K independently of C for now, and then just argue later that there is also a K which is large enough. And so let's look at just this equation. All I want is to find a C and a K for which this holds true, and K is large enough. How do I do this? So, first of all, I should rewrite this, right? So, what's the best way to rewrite it?
We can first remove the denominator. It's kind of an in number three.
Sure. So, and then I guess I can move it to this side and just take this. Okay. Now what? And let's just say M is more than N. Yeah. Without loss of generality. Now what?
We added both sides is congruent to same modulo 10.
Sure. That just
So if
gives
we
me.
have minus Cn is congruent to minus C mod 10.
That's obvious because D is a unit
Yes,
digit of Cn. Yes.
yes.
Hmm. And so what if N is a multiple of 10? What happens?
Then we can suppose for some large K and take other chords of 10.
No, but what happens to D?
D has to be also some multiple of 10.
D is a digit.
It's 0.
Yeah. So then what happens to the equation?
Like if n is some multiple of 10, then uh, we have uh, we have that d is smaller than 9. But on the other hand, there should also be some multiple of 10. So we get a contradiction.
So
That
10m is equal to n.
Yeah, but that makes no sense, right? I mean, because M and N are
Yeah.
given to us, right? And so it's something weird. So I mean, this idea. It seems like this idea doesn't work directly, but
If 2 or 5 don't divide n, then we can cherry pick k. We can just pick
yes.
k.
So let's see. So what happens if 2 and 5 don't divide N? So the idea. So the reason why we're considering this is because note that Cn is congruent to D mod 10, and so D is sort of free in the case N is not a multiple of 2 or 5, right? Okay. So suppose 2 and 5 are not factors of N. What do we do then? So we can just pick D, right? Just any D can work. We just take accordingly, just congruent to D times n inverse mod 10. Okay. And then,
We need a 10m minus n divides 10 to the k minus 1. And we just choose
yes.
k big enough, like k that satisfies that.
How do we choose such a K?
Whatever the prime factors of 10m minus n are, just p minus 1 of those.
Yeah. Or can you do something even more direct? Like all I need is 10 to the K is congruent to 1 mod 10m minus n.
Yeah, just 5 of 10 to the 10m minus n.
Yes. So that can work. So it suffices to take K to be phi of 10m minus n, because in that case this is a factor of this, right? And so for this K I can take C to be D times 10 to the K minus 1 upon 10m minus n. But is this sufficient? Like, are we missing something? Like we still need to guarantee this, right?
If 10 to the power k is 1 mod 10m minus n, then n's units digit has to be 9, right?
Also, to
Uh,
suffice the upper condition, we can take any multiple of phi of 10 mn minus n equal
yes,
to
sorry.
k, and it
Yeah,
works.
yeah, sorry. Meenakshi, can you ask me the question once more?
So like because 10 to the power k is 1 mod 10m minus n, isn't like n's last digit 9?
Why?
Because that's the only way it's possible.
Mm, why is that so? Because 10m minus n is a factor of 10 to the k minus 1, right? But I mean, factors of numbers of the form 999 can have other digits in the end, right?
Oh, right, yeah.
So, for example, 27 divides 999. Okay, yeah. So we still need to guarantee. Okay, so yeah, Anurag's idea is right. So we want to still guarantee that k is more than the number of digits in Cn, right? Uh, so the point is that I can take k to be any multiple of phi of 10m minus n as well. So let's say I take it to be some uh, alpha times phi of 10m minus n, and so my c would be 10 to the, okay, c would be d times 10 to the alpha 10m minus n minus 1 upon 10m minus n. And why is this true? Why is this true? Why is k more than the number of digits in Cn? By the way, I can just pick d to be 1, right? I can also pick d equal to 1.
Sorry to ask, but can you please explain when 2 and 5 does not divide and why 10 to the minus 1 divides 10 to the k minus 1?
Uh, I mean, uh, okay, so the point is that if 2 and 5 don't divide n, then I'm free to pick d. That's what I'm saying. Remember,
Yes,
we had a
yes,
problem that
yes,
if 10 divides n, then the issue is that d must be 0,
yes.
which is
D
absurd.
be some multiple of 2 or 5, or it must be 0. Then we use the dependency.
I mean, if n is neither a multiple of 2 nor a multiple of 5, then I can just really pick any d.
Yes,
That's the point.
yes,
Yeah.
yes,
Okay.
makes sense.
Okay, great. So uh, alternatively, we can view it as follows. If n is not a multiple of 2 and 5, then it is actually possible to make 10m minus n a factor of 10 to the k minus 1. Otherwise, it's not possible, right? Because 10 to the k minus 1 is neither a multiple of 2 nor a multiple of 5. So just to make this easy, if I could just make this a factor of this and ignore d altogether, my job would be easier, right? So 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 if 2 and 5 don't divide n, I can just pick d to be equal to 1 and pick a k such that 10 to the k minus 1 is a multiple of 10m minus n, which is not possible without this condition. Okay, so what I'm saying is that in this case, d equal to 1, k equal to some alpha times phi of 10m minus n, and c equal to 10 to the alpha phi of 10m minus n minus 1 upon 10m minus n works. Give If we prove that this is true, we still need to prove that this is true. How do you characterize the number of digits in Cn?
Log base 10.
Right?
Floor of log
It's,
base 10.
yes. So if I can show that k is at least 1 plus log Cn, then I'm done, right? Just let me know if you don't see why this is true. Just for example, how many digits does 3748 have? It has 4 digits. And notice that the log of 3748 is between 3 and 4. And so certainly 1 plus the log is more than the number of digits. So in fact, the number of digits in any such number. So for 1000, if you notice, it has 4 digits, and the log of 1000 is equal to 3. And so the way to find the number of digits is take to add 1 and take the floor. So actually the number of digits is 1 plus floor of log 10 cn. So it suffices to prove that this is true, right? And why is this true? So what is the log of cn? So we want to show that there exists an alpha. I mean, alpha is also something I can choose, right? So all I want is an alpha for which alpha times phi of 10m minus n is at least 1. Know that log c is just log n plus log c, right? So log n plus log of c.
I think it's easy to choose such alpha.
Uh, let's see why. Uh, why is it easy to choose such an alpha? Does there exist an alpha for which this is true? So okay, so I can also write this as this minus log of 10m minus n, which is 1 minus log of, okay, yeah, let's just keep it this way. By the way, these are very close because this is almost the same as this, right?
We can put alpha into 10m phi of 10m minus n be equal to some k. So we get that some k is greater
It
than
wasn't
equal
clear.
to log of.
So it wasn't clear what you chose your alpha as. Can you say that once more? Yeah, that's fine. Uh, okay, so yeah, so let's call this. So you're saying let's call this. I think I've used k. Yeah, okay, this is k, and so this is k. Okay, so we want this, right? Okay, yeah. And what next? K is greater than. Is that enough? Because this quantity may be more than 0, right? And so, yeah,
That part 10 m is greater than n, so then that'll be like log base 9, log base 10 of 9 n ish.
but there's a +1, which is a problem because
Yeah,
that's
but
log.
log base 10 of 9 plus log base 10 of n.
Like this would be 10n upon 10m minus n, right?
Oh.
Wait, this could be more than 0.
Yeah.
Yeah. I mean, okay, so we want to choose a k such that k is at least log of 10n upon 10m minus n plus log of 10 to the k minus 1. Yeah, the ceiling is k. Yes. Uh, so then, I mean, it seems like the inequality is not true, right? So
Shouldn't there be a floor around the log base 10 thing?
I mean, technically, there's a floor here.
Yeah, wouldn't that be good enough?
Hmm.
Because I'll cancel out the 1 approximately.
I mean, okay, so there's a floor everywhere here. You're right. Uh, Anurag, can you try to speak up exactly what you mean? I don't think I understand. Like, are you trying to disprove it or prove it? Like, okay. Yeah.
Actually, I'm trying to prove that k minus log 10 of 10 to the k minus 1 can't be greater than that stuff on the right until k is some very large natural
Which
number.
is fine. I mean, as long as there is one K, we're good with it, right? All we need is one such
But
K.
we get that if we uh, the minimum value of k minus log 10 to the 10k minus 1 will be 1, and the maximum value will be 1 and the minimum value will be 0. Which so we get that 1 is greater than some 1 plus log 10 of n minus log 10 of m minus n.
Yes.
So we get log 10 of n is equal to log 10 of m minus n.
Yeah. Yeah, you're right.
And we
So,
need to find it for, and it satisfies for all m and n. So it makes sense.
mm, not sure if I understand the last part.
Like then in the end we get that log 10 of n is has to be equal of has to be equal to log 10 of 10 m minus n. Then only this inequality will satisfy.
Yes, but what if I just want to prove it for one K? Like, does K equal to one work? I mean, I can't take K equal to one. That's a problem. Yeah. But like, okay. So I mean, I don't need to show it for large K, right? Can I can I find one such K that works? Or can we just not do it by this method? Or do we need to modify something? So the problem is that this inequality may not be true, right? It's not clear why this is true for any K.
Yes, because it is that the assumption of mine log 10 log base 10 of n only suffices when log 10 of 10 to the k minus 1 reaches its maximum value. But it is not every time it reaches the maximum value.
Hmm. What do you mean reaches its maximum value? Like, I'm not sure if I understand what that sentence means.
Like the difference of k and log 10 to the log base 10 of 10 to the k minus 1 can maximum can reach 1 at its maximal stage.
Uh,
And then we have that the left hand side is greater than 1. So it does not satisfy for all k and this
yes.
inequality.
Yeah, you're right. So, I mean, this approach doesn't doesn't seem to exactly work very well
Yes,
because
it works in some cases. We need
yes,
to fragment into cases and then it just becomes worse.
yes. So, yes, you're right. Okay, so the issue is that this may not be true for any K. So we need to try something a little different from this. I mean, it was close, but we need to modify the things we take here slightly. And so let's think of some other modification. Can you think of something as simple, or it could be something very different from this, but yeah. So instead of shifting one digit, can we think of something else? This could still work. I mean, yeah.
Wait, doesn't it work? Because with the floor, k greater than equal to 1 plus that, the inside thing will be like log base 10 of nd by 10m minus n into 10 to the k minus 1.
Hmm. Sorry, could you say that once more?
It'll be like Cn is Nd by 10m minus n into 10 to the k minus 1.
Yes.
And
So
Nd is
the
less than equal to 9n, and 10m minus n is less than equal to 9n. So then that part's less than equal to 1.
okay.
And then
Wait,
the floor will knock us to k minus 1.
let me write this once more. So I have n upon 10m minus n times 10 to the k minus 1. Yeah.
We also have a d, right? We have a d.
Okay, sure. Yeah, we have a d. Yeah.
And the first factor is less than equal to 1. And the second factor is fine.
Hmm. I mean, I can just take d to be 1. That's not a problem. I mean, a smaller d actually only benefits us.
Yeah.
Oh, true. It does work, doesn't it? Yeah. You are right. Wait. Hmm. Hmm.
But we'll only get exactly like greater than equal. We'll only get equal, I guess.
Which is fine, right? I mean, do we care if it's equal? I mean, do we need strictly greater? I think
I don't
greater than
think we do.
equal to, yeah, I think greater than equal to should do. Yeah, yeah, you're right. I think it's a little weird to me why this works. Did I make a mistake here somewhere? Okay, I have a floor here, right? I can just take the floor inside, which is not a problem. Uh, okay, yes, yeah, this will work. Yeah, yeah, okay. I mean, this makes sense. Yeah, okay, this will work. I think it's best to write it this way. So so this is plus 1, but notice that this is smaller than k and this is smaller than 0 because n is smaller than 10m minus n because n is smaller than m, and so this whole thing is smaller than equal to k minus 1, and so this whole thing is smaller than equal to k, which is what we wanted, right? Let's just take an example to see how this procedure worked. So uh, let's just let's just take n equal to 7 and m equal to 13, and so we wanted, okay, so we wanted this something to be 7n. We had a digit d and we wanted to move it to here, that D with this block is 13, sorry, 7C. This is 13C. So we wanted 13C to be equal to, and there are k digits here. Uh, if this is k digits, then I want uh, 7C minus D upon 10 plus D times 10 to the k minus 1. In fact, I was taking D to be 1, even more specific. And so this is equivalent to 130C equal to 7C minus 1 plus 10 to the k, which is equivalent to 123C plus 10 to the k minus 1. And so we took k to be phi of 123 and c to be 10 to the 123 minus 1. I mean phi of 123 minus 1 upon 123, which is quite cool. Yeah. And this should work. So let's see what these numbers are. Oh, it's huge. I mean, I guess. Okay, so it seems as if 13C looks something like 10569 up to 10569, and 7C looks like 5691 up to 56911, which is interesting. And yeah, I think that's what it is. And this one is actually moved here with a 0 here. I think that's what has happened. Yeah. Cool. Okay, so it's like this pattern's repeating or something. Whatever, it doesn't matter.
What happened to the one at the end? The 5691 one before it.
Yeah, that's what I'm thinking. Uh hmm, yeah, this should not have happened, right? I mean, this doesn't make sense unless I've put the wrong input here. Ah, no. Okay, so there's no one here. It's just this. Yeah. Yeah, I put the wrong input. It's 10569 here, and yeah, it's just this 505691 Yeah, it's just this blocks, and these are just these blocks. Okay, great. But we're not actually done, because we still need there's still a problem of this, right? We assume that n is not a multiple of 2 or 5. 5 of 123 is not 122, by the way, because 123 is not a prime. So 5 of 123 should be 80, right? Yeah, it's 80. Yeah, because 123 is 3 times 41. So the totient function is 2 times 40. Okay. So, okay, great. So, but now the issue is that it's possible for 2, 5 to divide n. What do we do in this case? So let's just take this again. So we had this equation, remember? We had c times 10m minus n equal to d times 10 to the k minus 1. And now what? How do we adjust? Like, what do I do about this?
As long as 10 doesn't divide n, we can just take care of it with the d. We can use d to cancel out that whatever that factor is.
Actually, no, because what happens if 25 is a factor of 10m minus n?
Ah.
So yeah, that's a problem because so even if 25 divides 10m minus
No, we
n,
can't
then
because m and n are, we can assume m and n are co-prime as was mentioned. So then we're fine.
It could still divide, could still be a multiple of 25, right?
Oh yeah. Okay.
I mean, it's yeah. So the problem is that it could be that I don't know something like 5 cube divides 10m minus n, in which case 5 cube must divide this, which is impossible because d is simply a digit, and 5 does not divide this, and so we need d to be at least 125. It forces d 0, which is not good.
It does not suffice if for some large element.
I mean, even if m and n are large, the problem of 25 dividing 10m minus n remains.
And we can find such element for such a 25. Some greater than 10 multiple of 5 or 10 divides it.
Yeah, I mean, we could always take m to be um, 18 and n to be 5 or something, right? And then 175.
Yes. And it is not possible to close these.
Yes.
Then d
Yeah.
should be 0.
Yeah, so d should be 0, but then that means c should be 0. And
Yes.
we're not allowing c to be 0. I mean, because c equal to 0 is always a solution. Okay, so I should say positive integer. I should have said that because otherwise it's trivial. Okay,
What
so
is the real approach of the real solution? Can you tell?
sorry.
What was the real approach of the solution?
The approach for the solution, I just tried simpler patterns. I mean this is something I just tried right now. I mean, I didn't know if this would work.
Not
In
this
fact,
one, I'm asking for the real one.
the what one? Sorry, could you say that once more? Oh, original solution. I don't know what they did in the original solution because I've not seen the original solution. Yeah. Okay, so yeah, what do we do here now? So so okay, so I mean, literally the approach fails. The problem is that if if any higher power of 2 or 5 divides 10m minus n, then I'm forced, okay, not for 2 but at least for 5, I'm forced to take d equal to 0, which and hence c equal to 0. So what can we do now? So okay, so clearly moving a single digit from the end to the start doesn't work here. So the single digit movement doesn't work. Doesn't work. So what could be the next step? So
I guess movement in any sense does not make sense. Because the approach would be somehow similar to this. We would be getting some powers of 10 and things. So it is better like we work in that block system.
yes. So if we work in a block system, what's the simplest thing you could do?
Like each block matches to the other block in the other number. Then we can easily go on to the
Yeah, but how do you work with the blocks? Like
like
what do you
I define the first block set A, and I define the second block set B. So I define a function f such that f is projective.
yes, but
F goes
like
from A to B.
yes, but numerically, how do you work that out? Because that would have many variables.
Like
Like
I'm asked. F like F takes out each block in the first number Cm and it tries to map out in the second number Cn.
Yeah, I mean, combinatorially, I get it, but I'm saying number theoretically, like the way we wrote this.
But we need to get some form of C. Then only we can prove that this is this.
I mean, we wrote something like this here. So I want to write something similar, right? So it's true that in general there will be permutations of blocks, but can I think, like, just think of something very simple, like just like this, just moving one digit. Think of something like that. Like, you need not think of permuting blocks
Like
everywhere.
moving the digit to the first place, we can move the digit to any place.
Yes, that is one possibility. So
Yes. To any place case is D. I'm I'm really lacking in variables. Any place A such that A is smaller than K.
yes. So what I could do is I can take this D and I can put it somewhere in between. That's a possibility. And I mean, I think it should work out. So we could try to work this out. So okay.
So we have proven it for 2 and 5 does not divide Z. Now we will try to prove it for 2 and 5 divides Z.
I 2 or 5 actually, not just and 5. So
Yes,
uh,
or
mhm. Okay, so Cn is some block of k digits where leading zeros are allowed in this k, right? And now I have some position. Okay, so what I do is I take this d and I remove it. So what that gives me Cn minus d over 10, which is some block, right? And then I split it somewhere and put a d here, right? So now it depends on where I split it from, right? So let's say I split it at the um, lth position, right? Uh, so by that I mean there are L numbers here and then K minus L numbers here. So what can I write this new number as? Actually, K minus L minus 1. Sorry. And now how do I write this number? Algebraically, like, just how would you have written this number? Like from here to here, I set Cn minus d over 10. What about the next step? It might be a little annoying and may need more variables, which is fine. Okay, what is this in terms of Cn minus d over 10? Let's call this A, right? So if this block is A, then what is this number? Is it clear what is going on? So I'm taking a block of numbers. Let's say this part is A and I don't know,
can
this
I
part is
tell
B.
what it will be?
So all the I'm doing is putting the D between B and A, right?
Can I tell what will be and Z will be?
Yes.
Like B will be equal to we will have Cn is equal to Cm is equal
I
to 10
I mean, yeah, yeah. Go on.
Cm is equal to A plus 10 plus 10 to the L minus 1 into D.
Just 10 to the L, because there are L numbers here.
Yes, yes. And plus E n minus A into plus n minus A into 10 to the
N minus A. Oh, this minus A, you mean?
yes.
Yeah, so it will just be Cn minus T over 10 minus A times 10, right?
Into the
Just into 10.
yes. But
Yeah. Is this clear? Just I just want to make sure if this is clear with everybody. Here, A is the last L digits of Cn minus T over 10. Right? And so what does this simplify to? Cm is A plus D times 10 to the L plus Cn minus D minus 10A, which is equal to D times 10 to the L minus 1 plus Cn. I think this, yeah, this, I hope I'm not making a mistake here. Yeah, this is fine. Cn minus 9A, right? So this means C times M minus N plus 9A is D times 10 to the L minus 1. And now how do you deal with this A? Because this A depends on Cn. So in fact, there's a way of writing the last L digits of a number in terms of floor functions. It's quite annoying actually the way you write it. So like if I have a natural number n, how do I write its last L digits? I look at the remainder when I divide it by 10 to the L, right? Is that clear?
Yeah, x minus 10 to the L into x by 10 to the L floor.
Yes. So the idea is that the last L digits is actually the fractional part of x over 10 to the L multiplied by 10 to the L. But this is just 10 to the L times the number itself minus its floor, which is equal to x minus 10 to the L times floor of x over 10 to the L, right? Which means I should be able to write this as C times m minus n plus 9 times Cn minus d over 10 minus 9 times 10 to the L times floor. So it's already getting a little complicated, which is equal to d times 10 to the L minus 1. So
it is better that we assign Cn minus D to be some k. Cn minus D by 10 to be some k.
I actually kind of want to simplify this, so let me not do that actually. So yeah, so let me write this as this, and then minus 9 by 10 minus 9 times 10 to the L floor Cn minus d over 10 to the L plus 1 equal to d times 10 to the L minus 1. Okay, and now, okay, so this 9d by 10 can go here, which is equal to d times uh, 10 to the L minus 1 over, okay, 10, right? So
I guess you can assign 10 to there to some number because it is independent of the.
Say that once more.
I guess we can assign 10 to the plus 1 to be some k because it is independent.
Sure. Yeah. Yeah. We can call it some T or something. Yeah. But now what? But now it's not clear how to deal with divisibilities, right? It's very annoying to deal with divisibilities in this case. Because it's like the additive sum of things. And so it's not clear what divides what here. It's still possible to find L, C, and D. I'm sure there should exist such numbers, but I'm not sure what to do here.
Maybe we should take things containing D2 ones.
Uh, I mean, I have another idea which should work, but I'm just trying to make this work. So my idea was to extend this instead of moving a digit here. I can just look at so what was actually the issue in the first solution? The issue in the first solution was that D was too small, right? D was restricted between 0 and 9, which is why whenever 10m minus n was a multiple of something
But
like
we can
25.
move any portion of the number.
Yes, so that's the idea that I think should work. So I will leave this a star because it is possible that this idea works, but I'll have to think about it. So I don't see immediately unless someone else sees an idea. So my idea is this. What we could do is we can move a bigger block in Cn. So we call this whole thing D, and I move this whole thing here. D. Yeah. And the same idea still works. That's the whole point. The point is that the exact same equation will hold true. So where is the equation? Yeah, so this equation still holds true. So I still have,
It is becoming more algebraic than number theorem.
yes, I mean, that is bound to happen. So, okay, so let there be, okay, so let the number of digits here be k. Okay, I should not use k, be t, right? So there are t digits here. Yeah. So then what happens if I move this here, right? And let's say the total number of digits here are k, right? And so what does this transformation do? Right. So first, if I remove the d, what that does is it makes this cn as cn minus d over 10 to the t. And once I move it to the very start, what this does is it adds 10 to the k minus t, right? And so this is my cm. And now I can simplify this as
And
cm,
the k minus t into d, right?
Yes.
yes, yes, times t. Yeah. So now Cm times 10 to the t is Cn minus d plus 10 to the k times d, which implies that C times 10 to the t times m minus n is equal to
See
d
how the
times.
power are changing. You can see the power is changing like with respect to we take number of digits of t. Like it becomes t here. It was 10 there. And
Yes.
you can still have some 2 to the t, 5 to the t. And this keeps fragmenting. So this does not work serious.
I mean, it could work. I mean, now you have choice over t, right? I mean, there's one more thing that you can choose.
Like we should have some 2 to the t dividing t, 5 to the t dividing t. If n is divided by some 2 to the t or 1 to the t.
Yes, but I can take t to be much larger than whatever the powers of 2 and 5 are in n, right?
But then we do not become independent of t. because the t has to be some multiple of 2 to the t or 5 to the t.
which is fine. I mean, I
But
don't see why that's a problem.
it does not satisfy us for all. It means it does not suffice us.
I don't understand. I just want to show one such CKTD, right? I don't need to show it for all, right? All I want to show is the existence of one such C, right?
But 10 to the t can't divide t, I guess, until it is 0.
But it can, right? Because D is a large chunk now.
But t is some like 10 t digit number. So at the end,
Yeah.
it becomes like 10 to the t minus 1.
Okay, so for example, let's say n is 125, right?
Yes.
What if I choose T to be 1000? Why can't I have a D with 1000 digits, which is non-zero and is a multiple of 125? Like I can just choose T to be very large, right? The power of
But I'm choosing n to be multiple of some 10 to the t.
okay, so let's say I mean no, you can't choose n depending on T, right? N is fixed. I can choose T depending on n, right? You can't change n, right?
Yes, okay.
Yeah, that makes sense. Yeah. Okay, so the point is okay, so here's the idea, right? So okay, so let the power of n in 2 be okay, so let p be the power of 2 in n, right? And let q be the power of it's bad choices of letters because these are usually primes. So let me use r and s be the powers of 2 and 5 in n, right? The idea is that if T is much larger than R and S both, then then note that the highest power of then note that the highest power of 2 in 10 to the t times m minus n is also R, and the highest power of 5 in 10 to the t times m minus n is also S, right? So all we need all we need is a d such that 2 to the r times 5 to the s is a multiple of d, right? And so I can just pick d to be equal to this. So right, so what I'm saying is pick
But then t will need to be some t digit number.
I mean I can just put zeros in the beginning, right?
Ah, yes, okay.
Right. I mean I this block can have zeros in the beginning and then have something. So which is fine. So pick t to be larger than max of r comma s and pick d to be equal to 2 to the r times 5 to the s. Yeah. So what does this do? What this means is I can write, so let me just rewrite this equation is 2 to the r times 5 to the s times 10 to the k minus 1. And I just divide 2 to the r times 5 to the s to get 2 to the t minus r, 5 to the t minus s times m minus n over 2 to the r, 5 to the s equal to 10 to the k minus 1. But now notice that 2 and 5 don't divide this. Do not
Yes, it is.
divide this. And so I can pick k to be phi of this quantity, right? Whatever this is. So and c to be equal to 10 to the k minus 1 over whatever. Okay, I should just call this something z o z. And you can check that this will work. And that's it actually.
Yes, it works.
and you can just check that the bounds will work out just how the bounds work out here in the first case. I, I,
So we
I'm
are getting proof.
I'm pretty sure this works. Yeah. Okay. Yeah.
Let's see
Uh,
what was the source of this problem.
I think this is USAMO. I don't know the year.
How the US and previous now.
I mean, USFO problems are pretty hard in my opinion, actually. Uh,
Like actually anyone would take some much time doing this work. Like we were proof solving and then we took like 1 or 2 hours, 1 hour doing this. Like 9 of us were solving this.
yeah. I mean, I guess it's fine. I mean, the point is, I mean, I guess the more important thing is like the takeaways, right? So, I mean, there are sort of
I guess
these.
there would I guess we could take any chunk of D and then we can also prove it for some 2 and 5 that does not divide an n. It can be also proven in this case. The first case, like we took D is the last digit, it is not importantly, we can also prove it in this.
Uh, um, I mean,
Like if we have 2 and 5 does not divide n, in the second case, when we are moving the chunk of D into any position, into the front,
yes,
then we can easily prove we have 10 to the D and minus 1 dividing 10 to the K minus 1. And D is
yeah.
independent.
Hmm.
It is the sum of similar.
Yeah. I mean, if you do this case, then you don't really need the first case. That's what you're saying, right?
Yes, yes, yes.
Yeah. Definitely. Yeah. This case is not needed once you dealing with this case. Yeah. But the whole takeaway is that if I mean, I feel like the takeaway from the problem is that just try simpler things, like simpler, add more restrictions, honestly, add more restrictions and look at like a very specific sort of structure. Like the problem itself only asks for permutation of non-zero digits, but we could, I mean, we only just shifted last to front. So like that sort of things always like work out many times. And yeah, just general, maybe just think of special cases more, just how we thought about the not equal to 2 5 case. Like even if this comes in the exam and you can prove this for n not a multiple of 2 and
I
5, and
guess
you
it
can,
took time for the root idea. If we firstly considered the moving the chunk, then would have been easier.
yeah, definitely. I mean, uh I feel like the 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 hardest part of the problem is to even consider something like this. Like I think
Yes,
I,
and the other part is easier.
yeah, I mean, this the algebraic part is not as bad as actually thinking of what to consider. So yeah, so yeah,
If
that's true for
is
almost
having
all.
large algebraic intuition, you would have already guessed before that we should consider moving the chunk and moving the digit.
Yeah, also the whole point is that moving the last digit to the front avoids things like introducing more variables like a here. I think that
Yes,
could be
this
one
becomes a
reason.
bit of painful,
Hmm.
but the other one is easier.
Yeah, definitely. And I guess some motivation could come from decimal expansions maybe for this problem, but it's fine. Think the correct lemma is, I mean, okay, I mean, these are easier said than done, honestly. So um, yeah, I just feel like this is something that's important, right? Just you can always add more hypothesis and make your life easier, but sometimes it may not work, which is fine. Let's just do one more problem and then we'll end today. Let me look at a problem because I've run out of problems in my head. Um, Sorry, maybe we should end here. It's been like 2 hours. Okay, yeah, we can just end the session here today. I forgot about the problem set because I've been. You can stop recording, by the way. 1 second.